Okay, I'm going to continue with chapter 1, data representation and storage. And the point here is that, how um, a computer works with information in terms of like if it's data or if it's a computer program. However, at its lowest level, a computer is just works with a sequence of ones and zeros. And they're called binary digits. We're used to a number system, base 10 number system. With computers, it's either a state, you have one bit or one tiniest piece of information, or at the lowest level, information is just either an on or an off. Okay? So, since that's the case, what we want to do is we want to look at ways in which you can actually represent information. Maybe you can represent characters or you represent numbers. Um, if you think about it, how do you represent negative numbers, positive numbers, fractional numbers, right? A computer has to be able to do that. And it does it just by this sequence of ones and zeros, okay? Now, when we talk about computers, typically we don't say the number of bits. Typically, when we're talking about like how much RAM memory or how much data storage you have, like on your hard drive or your SSD, we refer to that in terms of bytes. And a byte is just a sequence of 8 bits. So it's just you're taking basically a group of 8 bits and calling that one byte, right? And modern computers, we talk in terms now of gigabytes and terabytes. Okay, gigabyte is 1 times 10 to the 9, a gigabyte number of bytes, which means 1 times 10 to the 9 bits, and at least essentially it's approximately that. Um, since it's in base 2, it's close to that, so we should just say that. And in terms of terabytes, that's 1 times 10 to the 12 bits or bytes. Okay, so a byte is just a sequence of these 8 bits. All right. Now, one of the things, just to give you a little bit of information behind this, so the way a computer works in terms of its memory, right? One of the things I talked about previously was that, a computer program gets loaded into RAM memory and then it executes. Essentially, the brains of the computer, the CPU, executes that. Well, to know where information is stored, there's a thing called memory address. Okay, and the way it works is that if your computer's executing some code, what it will do is it will go into RAM memory to find specific data or part of a program. And what it does is it uses a number, which is just a binary sequence. So in this case, 3 bits are used to represent the address. Addresses, of course, in a real computer could be 32 or 64 bits now is common. But that just tells it where a particular piece of information is. And this is what the central processing, the brains of the computer uses. So it says like, its basic idea is what it does is it goes to a certain address that's defined in the program and says, go and get the data that's there. And the data could be, part of your, could be like a document, part of a document, or it could be part of a program. Okay? And depending upon how your program is written, it will use that process. Okay. Now, that's kind of a quick overview of like how it actually goes through this process: fetch, decode, execute is what it's called. That's a quick overview of how the CPU works. But the important, really core part of this is for us to understand is that even though we see these address numbers here, right, the real inside the computer, it just sees a sequence of zeros and ones. Okay, and in this class we don't really talk about how that information is stored, but just recognize that at its lowest level, it's just a 0 or 1. Okay, so we need to talk about, and part of this class is like, how do you get from this sequence, zeros and ones, to a number like this? And if you notice, these are just like base 10, or base 8 is actually also valid. But base 10, which is what you used to, right? Base 10 just means using symbols 0 to 9, 10 symbols to represent a number, right? With base 2, there's only two numbers. There's only two symbols, 0 and 1. Okay? Now, just kind of briefly to show you how this works, is that over here, I won't worry about this. This is just kind of an example. It's just random numbers put in here. But over here, this relates to this number. So if you have this number and you add 1 to it, if you're in base 10, you would just get 1. But if you're in base 2, you get 0, 0, 1. All right? Which is essentially the same thing, if you're adding 1. But the difference occurs here is when you go from 1 to 2. Well, what happens here is that in base 10, you go from 1 to 2. In base 2, you add 1, and then you carry a 1, right? Because you ran out of symbols. In base 10, if you had 9 and you added 1, you'd go to 10. In this case, you go to 1, 0. Okay, what you need to recognize is this is base 2. Okay, so what it says basically, I added 1. I ran out of symbols because I only have 0 and 1. So when I add 1, I put 0 down here and I carry a 1 over. So this is 1, 0, 0, 1, 0. This is 1, 0, base 2. Okay. And in this class, I'll use a subscript of 2 to make sure that it's very clear, or say very clearly that it's a base 2 number. Okay. Then the next one is you add 1 again. And then you see what happens here is that it just becomes 1, 1, right? So we add 1 here. And then now what happens when we add 1 again? We ran out of symbols here, right? We carry a 1 over. We ran out of symbols here. We carry a 1 over. And now we have 1, 0, 0. Okay? And that's basically how you count and how it relates direct back and forth between the two. All right? Okay. Just a little bit more terminology. Now, we'll talk more about this, but let's say you had an address. I forget what this. I think it was 16 bits. 4, 4. Yeah, about 16 bits. 1, 2, 3, 4, 6, 7, 8, 9, 10. Yeah, 16 bits. So if you had a 16-bit, let's say this is a 16-bit address, or sorry, value stored at a 16-bit address. Let me rephrase that because it's not actually what it's saying. It's a 16-bit number stored at this address. Okay, so it's 0, 0, 0, and this was your number that was stored there, 16-bit data value. Okay, you could actually translate that to 2781. All right, base 10 or 2781. And that's one of the things we're going to talk about is how do you go from something like this to something like this. All right, so that's important. And I will say that, in terms of programming in this class, that we're going to get a brief overview of, I'm going to give you a brief overview of, working in the two number systems and how to convert back and forth between them. But not too much detail. We only have part of the chapter 1 that we do that. And after that, it's like you get a rough idea of how this works and, some of the specifics behind it. And then we'll just be, of course, writing code afterwards, okay? So it's a good idea to understand this and, not understand all aspects of it because it gets to be a bit more complicated, but at least enough to have a good appreciation for it. Okay. Okay, so here we go. So how do these number systems work? Base 10 number system. What is it really, right? All we're saying here is this has a weighting of 10, of hundreds, tens, and ones, right? So if we were to say, how could we rewrite this number? It would just be 2 times 10 to the 2, which is this one, plus 4 times 10 to the 1, which is this one, plus 5 times 10 to the 0. Okay? And that's not too hard, and you can, and the reason to represent it like this is just to show you that we have an analogous system when we have analogous approach when we talk about the other base systems. Okay. So here we go with base 2. So the same thing as what we did previously, except now we have to think about it in terms of base 2. So this is 1 times 10 to the 0, 1 times 10 to the 1, I'm sorry, not 1 times 2 to the 0, 1 times 2 to the 1, 1 times 2 to the 2, 1 times 2 to the 3, or 0 times 2 to the 3, and this would be 1 times 2 to the 0. Okay. Okay, continuing on. Now we have base 2. Okay. And it works the same way as previously. This has a weighting of, base 10, but now it's base 2. This is a weighting of, um, you know, uh, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and this is 2 to the 4. Okay. Well, if you wanted to go and convert this to a base 10, all you have to do is just do each digit or each digit in this base 2. See the subscript here, it's base 2. It's going to be 1 times 10 to the 4, the 0 here times 10 to 2 to the 3, 1 times 2 to the 2, 1 times 2 to the 1, and 0 times 2 to the 0. Okay, so if we go through and add them up, we now have the equivalent in base 10. So this is basically how you go through the process of converting from base 2 to base 10. Okay, and this is what's actually happening behind the scenes. The computer is going through the process of making this conversion, and when the computer is working on the information, it actually looks like this. What you see is this when you run your program. What you recognize here is that when you have a number like 22, and let's say that's in your program, it's actually going to be stored like this. Okay, there'll be a bunch of zeros out here on the left-hand side, but that doesn't impact the magnitude of this number. Okay, so recognize that. So this would be the process of going from base 2 to base 10. Okay. Now another number-based system that is important for us to look at is base 8. Okay. Now base 8 is just now, this is, this has a weighting of 8 to the 0. This one has a weighting of 8 to the 1. This one has a weighting of 8 to the 2. Okay. So we can go through the same process here. We can do it 2 times 8 to the 2 plus 4 times 8 to the 1 plus 5 times 8 to the 0. And if we just take and add those all together, we come up with 165 base 10. So if you started with a base 8 number, 2, 4, 5, base 8, you would get 165 base 10. Okay. Now, base 8 is just using symbols from 0 through 7. So there's 8 symbols, right? If it was base 16, how many symbols would there be? There'd be 16 symbols, okay? So, and it would go from 0 to 15, right? But what you recognize is when you're doing base 16 is that we run out of symbols, right? We go up to 9, and then we have to have new symbols. And what we do in base 16, which you'll see a little bit later, is we use A through F to represent essentially, decimal 10 through decimal 15. Okay, but this is just briefly how you go about and convert from base 8 to base 10. Okay, here's base 16. So in base 16, we ran out of symbols. So what the symbols that were chosen at 9, we ran out of symbols. A, B, C, D, E, and F. Okay, so it works the same as before. This has a this is a weighting of 16 to the 0, 16 to the 1, and 16 to the 2. So if you go through the math on this, this becomes 16 to 2 is just 256. 16 to 1 is just 16. Of course, anything raised to the 0 power is just 1. And now we have 512 plus 240 plus 11. So this, in base 16, also called hexadecimal, is this in base 10. Okay. Now, one of the things we may want to do, and one of the things that happens is like, oh, okay, that shows you how to go from base 2 to base 10, or base 8 to base 10, or base 16 to base 10. So now, if we wanted to go in the other direction, what would we do? Well, we could use long division to do that. All right, and then we don't have a fraction apart, we just use a remainder. And we do long division by 2 because we're trying to go to base 2. Okay, And each time we have, a result of the division, the whole part of it, and then the remainder. And the remainder is actually what we're going to use to generate our final base 2 number. Okay, so let's say our example, we have 26, the number 26 base 10, so it's base 10. And we start through this, and we want to take that 26, and we want to figure out what it is in base 2. Okay, so we just start. We just keep dividing by 2 each time, and we keep the whole part and the remainder. And the remainder, like I said, becomes the number. So first thing is we divide 26 by 2. We get 13. And we carry that 13 down again. We divide by 2. And we also take that remainder and we make it our least significant bit on our number. And we do it again. We get 6. We do it again. We get 3. And we keep retaining the remainder each time. And then we keep doing it until finally our whole part of our division becomes 0. And that's when we stop. And we have a remainder. Okay? So once this becomes 0, that's essentially it. We got to the end. Right? And then you take this number and basically just slide it down, right? So this is our base 2 number. And it's 1, 1, 0, 1, 0. And this is our least significant bit. Now you can prove this to yourself. You can just actually go through the math and show that this is actually 26, okay? All right, so this would be 0 times 2 to the 0. 0 times 2 to the 1, so this is just 2. 0 times 2 to the 2, so we still have 2. 0 times 2 to the 3, so this is 8. Okay, so we have 2 and 8. And that's 3. 1 times, this would be 1 times 2 to the 3. And this is 1 times 2 to the 4. So this is 16. This is 8. And this is 2. You add those 3 together, and you come up with 26. Okay? So you can go back and forth. You can see it's easy to go back using the previous technique to get that number. Now, if it was base 8, what you could do is you would just divide by 8. And the remainder would be between 0 and 7. Okay? And you could do the same process. So you have this, divide by 8. Whatever number it is. So if you did divide by 8, then you would have divide by 8 again, and however far until you finally have 0 as the whole part and a remainder. Okay? If it was base 16, you just divide by 16 each time. 16, 16, 16, 16, and then 16. But in this case, of course, you're not going to get all the way down here. You're going to end up basically when you're here, you'll be essentially done. Okay, and with base 8, you're not going to have this many divisions. You'll have just up to like here or here. Okay, so it's you won't go down as far. You won't have as many divisions. Of course, the divisions are more complicated. Okay, so recognize that long division to convert between number systems. Okay, so going from base 10 to base 2, use long division. Follow this process. Except if you're doing base 8, this becomes an 8. And you do the same process, and like I said, until you get to be 0 as the whole part of the number. Base 16, you follow the same process. Okay? All right. Continuing on. Okay, so you can actually go through and do these examples. All right? So this one is, 3, 7, 1, 6, base 8. And what I'm going to show you here, kind of real briefly, I'll show you what you can do with the calculator. All right, that can actually go in and check your work. So you can actually go through and do the same process with these from what we previously did, right? But let's go and I'll show you how to do that with a calculator on. So the calculator app. Okay. All right. So you have scientific notation. I'm sorry, scientific calculator. The calculator that I want is the programmer calculator. Okay. So you can select that, programmer. And now what I want to do is you can actually go up here and select which, is this number that you're creating, is it hex, is it decimal, is it octal? Octal 8, hex is 16. This is, base 16, base 10, base 8, and base 2. So let's take an example here. So let me look at a number. 3716, base 8. So that's an octal one. So I click octal. So then I do 3716. And then oh, sorry. Well, in this one, you actually don't need to click calculate. If you have an older version of Windows, it may look a little bit differently, and you might have to click the button. But what you'll notice is right after I type this in, I think so, right? What happened here? Let me clear it first and do one more time here. 3, 7, 1, 6. Yeah, so this calculator, on this calculator, it actually shows it over here to the left what the numbers are. So here it is in hex, that number, decimal, octal, and here it is in binary. Okay, so as you go through and do these, you can actually just check your work. Now, I probably will give you a quiz at some point where we'll go through and you'll have to do some of these, but you'll have to show all your work when you do them. So it's more than just using the calculator. Of course, you're at home, you can, or wherever, you can always just check it, verify it, but you'll have to show your work. Okay, so here are the numbers and the different values. So this one actually asked you to do it in base 2. So you should go and do it and just verify that you come up with this number. Okay, so any of these, right? This is base 16. So 3A16, let's do that one. So I click hex. 3A16. Okay, and here it shows you what it is in decimal, what is in octal, and what it is in binary. Okay, so this one just asks you to do it in base 2. Okay, that's a little bit of work. It's good practice, to get to that. Right, now I'm going to show you one other thing about this that will simplify your work. And I'll go back. Let's go back to this. So like I said, that's how you use the calculator. Let's go back to one of these previous ones from the current slide. Okay. Do this. Okay, so here we go. Let me go back here. I want to take a look at something here. One of the things you'll notice is that if you look at these numbers, here's my base 2, and here's essentially base. It's really base 8, base 10, they'll come up to be the same. Or base 16, well, actually up to this point would be the same. Is that, look what happens here when we get down to base 7. We have now run out of symbols. Okay? So what you'll find is that you run out of symbols after 3 bits in base 7. Okay? So what it really is telling you that is you have this thing called grouping. You can group the numbers as 3 and groups of 3. So like if I had a number like it was 2, 7, let's say, it would be 0, 1, 0, 1, 1, 1. So you can actually make the conversion between each group of 3 digits. So if you're going back and forth between base 2 and base 8, it's just a grouping of 3 digits. When you're going back and forth between base 2 and base 16 is a grouping of 4 digits. Okay? So I'll show you this process here kind of quickly. We'll do it on one of these just to show it. One of these examples I gave you. Okay. So in this particular example, let's say I wanted to make the conversion between 3716. What you can do is you can come up with the symbols. Okay, you come up with the value for this one. Okay, so just to show you that, it would be 0, 1, 1 would be this 3. Okay, so if you converted this to base 2, it's just 0, 1, 1. Then the next one, 7, is 1, 1, 1. And then this is just converting it over to base 2. This symbol here is 0, 0, 1. Because we're doing it, since it's base 8, we're grouping them in three symbols or 3 digits. Okay, and the last one, 6, is just 1, 1, 0. Okay, so the base 2 for this one, when you get 3, this is 0, 1, 1, 1, 1, 1. This one becomes 0, 0, 1, and this is 1, 1, 0. So the whole thing is 0, 1, 1, 1, 1, 1, 0, 0, 1, and 1, 1, 0. Okay, so if we just go back to the calculator, I'll show you that. Go back to the calculator, clear it, and we put this in. So we are in base 8. Start with octal. I'm going to put the number in 3, 7, 1, 6. Okay, so if you took it as 3 bits at a time, this represents the 3, the first 3 digits. Look at that, 0, 1, 1. That's 3, base 10, not base 16. And then the next, base 8, sorry, base 8. Then we take the next 3 digits. This one, this one, this one. These next 3 become to 7. That's my 7. Then the next 3, 0, 0, 1, which is 1. And the last 3, 1, 1, 0. That's my 6. Okay? So this is a grouping technique. When you're doing from base 8 to base 2, or back and forth between the two, you handle it as 3 bits at a time, starting from essentially the left or the right, and you just write it down. The 3 bits represents each digit. Then you do the next 3 represents the next digit. Then the next 3 represents the next digit. And the rest 3 represents the next digit. Okay. Now, we can also look this as, let's assume that the number was 7CE. Okay. This is 4 digits. So the first 4 digits become the 7. The next one is our C. And C is essentially, 12 in decimal. And the last 3 are E. And E is 14 in decimal. Okay? So it's very easy, actually easy the way this number is represented to see it in terms of hex and binary. Okay? So at this point, and I'll give you some, I'll work through some other examples, and I'll give you some more videos, and I'll find some other videos for you to see these things worked out in more detail. But the basic idea is you use the grouping technique to go back and forth between base 16, base 8, and base 2, back and forth between any of those. You use the grouping technique, which I just described. Okay? All right, so let me close this out, and we'll continue on. Okay, here we are. Okay, now one more topic related to this is the data types. Okay, now how this kind of ties back to or how it ties into C++ is that you have certain kind of you have everything's ones and zeros, right? And your programming language, or the program that you have, when your program executes, it needs to know what that information represents, okay? Because it's a bunch of ones and zeros in memory. So what you're going to see is that when we start to write code in C, and C++, is that we have to tell the program how to store the information and how to interpret the information, okay? So in the program, if we are putting a number in memory, we have a specific type called the integer data type to handle those. Okay? All right. And how is it actually represented? If you drill down into memory and looked at the bits that are in memory, what would happen is that if you would see a sign of the number, and then 31 bits would be whatever the magnitude of it. Okay? So the leftmost bit becomes the sign telling it whether or not it's positive or negative. If it has a 1 in the leftmost bit, which is the most significant bit, it's a negative. If it's 0, it's positive. Okay. And like I said, when we actually start to write code, how the computer handles data in the background really is not as it's to be a successful programmer at this level, whether or not what happens in the background probably is not that important. As you move along as an engineer, then yes, definitely you need to know. Okay. Like I said, though, to be successful in this class, if you got a rough idea of how this works, that's probably about all you need right now. Okay. Okay. Now, data types. Now, one of the things I didn't mention, we only looked at whole data, not whole numbers right now, is that we also have to be able to handle negative numbers. And the way we do that is we create, if a number is negative, we can make a conversion. We follow this 2's complement conversion process, which I'll describe shortly. And we call that 2's complement form, okay? So just to give you an idea, is that if a number is negative, we go through this 2's complement process to convert it. If a number is positive, we don't go through the process converting it. But both are in 2 complement form, okay, or 2 complements form. All right, so recognize that if you have a positive number, when it says 2's complement form, it's the same thing as if you had a whole number. Okay, so there's no change. Only when it's negative, we've got to go through this thing called 2's complement conversion. Okay, so I'll just give you. Okay, the next is floating point data. And floating point data types. What you're going to do is you have a fractional part, essentially, right? Now, in C++, we have to identify if a number is an integer or a floating type. Floating type, we have 2 different ways to define it. One we call float, and the other ones we call double. Okay, but the basic idea is we have to essentially tell the computer, hey, this data that's stored in this location, or how it's being stored in this location, is a number that has a fractional part. Okay. And the way it's done is a little more complicated than this, but the basic idea is what it does is it takes like that sequence of however many bits, and then it just assigns part of it to be like the actual magnitude, and the other part to be like the exponent or fractional, not exponent, but for the fractional part. Okay. How it actually works is it has an exponent. It's a little more complicated than this, but this is a basic idea, right? The basic idea is setting it up like this. So the way you would handle it is this becomes, and I'll get some examples for you, either create or find some good ones for you to show you how this is done. But the basic idea is that you have the whole part of a number and the fractional part of the number, okay? And that the whole part gets converted just like before we saw previously to binary. And the fractional part, what you recognize is everything to the right of the decimal point becomes like this is the it starts with a factor of 2 to the minus 1, 2 to the minus 2, and 2 to the minus 3. Well, 0.25 is in this case is 2 to the minus 2, so it's like 1 times 2 to the minus 2. So the number would be, if you had, let's say it was 8 bits, it would be, and 5 bits were the whole part, and 3 bits were this, it would be 0, 0, 0, 0, 4 zeros, and a 1, okay? And then to the right of the decimal point, for the last 3 bits, it would be 0, 1, 0, where 0, 1, 0, a dot, 0, 1, 0. So it'd be like, the whole number would be 0, 0, 0, 0, 1, dot, 0, 1, 0, okay, if it was in base 2. All right. So like I said, I'll get you some examples, show you how it's done. But it's the same basic idea, except we define a decimal point, and then what we say is whatever's to the right of the decimal point is, has a weighting of 2 to the minus 1, 2 to the minus 2, 2 to the minus 3. And everything to the left of the decimal point has, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3 is the weighting. Okay? All right. The other thing is 2's complement. And 2's complement is a process where you go through and convert a number to this 2's complement notation. Okay? So what you got to do, the basic process is this. You take the whole part of the number, you convert it to binary. Then, after that, after you convert it to binary, what you do is you convert it to binary, you invert all the bits. All the ones become zeros, all the zeros become ones. Okay? Then you add 1 to it. Now that number is your 2's complement number for this. That represents minus 47. Okay? And you can actually go through and just plug minus 47 into the calculator, and you hit make sure you're in decimal, and then you'll see the 2's complement form being listed in binary. Okay, so when you go through this process, 2's complement, you'll find out that you can check your answer. Okay, when you have a positive number, the only thing you do is convert it to binary, and that's it. And then now it's in 2's complement form. Okay, so 2's complement form for a negative number, go through the 2's complement process. 2's complement positive number, you just do the conversion to base 2. Okay? All right. And you can check this work. Like I said, I'll get you some videos on showing how that's done. Okay. Here's a base. Here's the floating point type where you have a fractional component. And you can actually go through and do this process, and it's the same thing. You could do the fractional part and the whole part with that. Calculator doesn't support like the fractional part separately. So, but you recognize this one is going to be 0.01. This one is going to be 0.010, of course. Then this one is 0.011 for the fractional part. Okay. All right. So I'll get you another one for that too. Get you a video and some examples of that. Okay. So there's one last part here we need to talk about, is that when you're dealing with like word processor, text documents or whatever, you have characters. So you have these other things. We have other symbols. So you have characters that are represented too that aren't numbers, right? We have to be able to handle that. And the way it's done is with this. There's a table essentially in the memory. And it goes through the process of making the conversion. Okay, so there's data type that you use when you're dealing with characters in your programs. It's called CHAR, and we'll see how to do that. But the basic idea is we want to see how this is done. So the way it's done is there's tables, and ASCII and Unicode is used to handle characters. Okay. So Unicode is just like an extension of ASCII. ASCII is basically the translation. Okay, so here's ASCII. What it is, the basic idea is just an encoding, okay, and decoding. All right, so here's the ASCII code chart. So if you specify that in your program you want to deal with characters, what will happen is that a conversion process will be done. It will take that number, and you can think about it in terms of, hex. You can think about it in terms of decimal, binary, base 8 if you want. It doesn't really matter. But if we look at it in terms of decimal number, okay? So we look all the way down here. We're looking at the decimal values. We can also, like I said, hex. But let's say we take a look at 0. Now, 0 is also a number, right? But in this case, if we're thinking about it like in a text document, if we wrote, we typed in 0, it would be handled as a character. Okay. So the translation for that is just 48 decimal or 30 hex. And you can actually go through the conversion process and you would find that 48 decimal does equal 30 hex. Right. So let's say if we had an uppercase A would be a 65, would be stored in memory, 65 in decimal, but it could actually be binary stored in memory, but you can go through the process to see what that is. And that would be an uppercase A. And then if you notice over here, we have lowercase a. So they're actually different. So the whole point here is that Computers also deal with characters, right? So you have to have a way to handle characters. And it's done through this table, translation back and forth. And this is ASCII. And there's a lot more symbols than that, of course. Things have expanded a lot further, and it's actually part of Unicode standard now. Okay. So this is how it's done. Pretty straightforward. You know, you could actually go through and you know, you can, oh, there's like software, there's things online you can check. So you could say, what's the ASCII representation of something? And then once you see how it's done, it's pretty straightforward. Okay. Okay, so here's Unicode. Unicode is just essentially an extension of this, all right, of ASCII. And it just tells you some of the differences. Unicode supports far more characters in different languages. It really is, I don't know what their standard is now, but they use a lot more character. They use a lot more bits to represent the characters. We only have 7 bits. If 7 bits, you could only go up to 128 characters. You could only represent 128 unique characters with the 7 bits. So that's a limit. But Unicode is based on ASCII too. So ASCII is like the lowest part, the lowest, the rightmost or least significant 7 bits. Okay. All right. So that basically summarizes it. Ones and zeros. That's all computers are based on. Okay. It would be really difficult for us to go through and you know, work with just ones and zeros. That would take us a long time to write any code or work with a program. That was originally how it was done, of course, but ones and zeros would take a long time. So we have these higher level languages now that do all the translations for us. And I just went through and briefly talked about a few of the different translations, you know, like ASCII back and forth for your have a character, and the number systems, like if it's a floating point number or not, and how do you handle negative numbers. And there's a lot more if you can think about it. You're like, well, what about math, right? It's like, how would you do math operations? You know, how do you do addition's not hard, but how would you do like multiplication, division, right? And with positive numbers, with negative numbers, with fractional numbers, you know, or whole numbers. So it gets to be a bit more complicated, but in this class, we're not going to cover any of those. We're just going to stick with some of the basics just to give you some of the basic ideas, like the ones I covered. Those are really the only ones you're going to be responsible for. Okay. We also talked about, you know, integrated development environments, and visual community is the one I'm going to use in this class, and you can use others if you want. Okay. And like I said, with octal and hexadecimal really are just useful because they allow us to group bits, 3 bits, 4 bits. Okay. And that is about it.